Hey there, this is the video for Chapter 7, Section 3. We're going to be working with t distributions again for this section. So if you want to refamiliarize yourself with the calculator function inverse t, that will help you. We're going to be adding a new calculator function too. It's on your lecture notes, but if you have a special place you're putting your calculator notes, make sure you add it there. It'll come towards the end of the lesson. Also, if you have the t distribution tables printed out, get those out too before we get started. That's Table 5 and Appendix B. Okay, let's dive in. Welcome to the lecture video for Chapter 7, Section 3. Today we'll be talking about how to find critical values in a t-distribution, how to use the t-test to test a mean when sigma is not known, and how to use technology to find p-values and use them with the t-test to test a mean mu when sigma is not known. Okay, let's get going. So this test is in contrast to the last one because we don't have population standard deviation. But as we've said before, it's not likely that the population standard deviation will be known if the population mean is not known either. However, there is a way around this, which we've worked with before. That is, if the population distribution is known to be normally distributed, or the sample size is greater than or equal to 30, then we can still test the population mean mu with a t-distribution and n-1 degree of freedom. When we're finding critical values in a t-distribution, we need to do a few things. We need to specify the level of significance alpha. We need to identify the degrees of freedom, n-1. We need to find the critical value using the table from Appendix B in your e-text. You'll see the one-tailed and two-tailed tests labeled on the t-distribution chart. For a left-tailed test, we just use the negative t-value. For a right-tailed test, we use the positive t-value. For the two-tailed test, we use both a negative and a positive value. Let's walk through how to read the table. At the top is listed the level of confidence. Sometimes the number you need will be listed this way. Sometimes it's listed as alpha. They're just different parts of the same number. If you've been given alpha, the next thing you have to determine is if it's a one-tailed or a two-tailed problem. If it's one-tailed, you'll use this next line's numbers, and the resulting number you use below depends on whether it's a left-tailed or a right-tailed graph. If it's a left-tailed graph, you'll use a negative version of the number you find in the table. If it's a right-tailed graph, you'll use a positive version of the number you find in the table. If it's a two-tailed graph, you'll use this next line's numbers, and you'll use both the negative and the positive versions of the resulting number below. After you have decided whether you have a one-tail or a two-tail, then you have to look at degrees of freedom along the left-hand side, and then you have to match them up. I'm going to pretend I'm doing a problem that has a right-tailed graph with alpha of 0.05 and n equals 3. So n-1 equals 2, so 2 degrees of freedom. Don't forget to do that -1. So I'm going to look down from 0.05 and across from 2 degrees of freedom to find my resulting number, which for this case is 2.920. And because it was a right-tailed graph, we'll use the positive 2.920. If it had been a left-tailed graph, I would have made that a negative. If it had been a two-tailed, I would have used both negative and positive 2.920. Okay, let's do an example. Find the critical value t0 for a left-tailed test given alpha equals 0.05 and n equals 21. So I can do this two ways, but first I need to identify my degrees of freedom. N equals 21, so my n-1 is 20, so my degrees of freedom is 20. Next I look at alpha, it's 0.05. So at this point I either look at the table or use my calculator. Let's start with the table. To use the table I need to identify the appropriate alpha. It's 0.05, but am I doing a left-tailed or right-tailed? It's told us left-tailed, so that means my result will be a negative number, and it means I'm going to use the row that says one-tail alpha. So I find that spot and follow it down. Then I find my row for degree of freedom of 20 and see where they intersect. And remember to make my result a negative number. Now if I wanted to do this on my calculator, I would use the inverse t function. I would press the second button, then bars, then arrow down to or press 4, the inverse t function, Then I would put the area in decimal form, in this case 0.05, then press enter, then put in the degrees of freedom, in this case 20, then press enter as many times as needed to calculate. Either of the ways that you do it, you should come up with 1.725. Okay, let's try another one. Find the critical value T0 for a right-tailed test given alpha equals 0.01 and n equals 17. So using one of those methods, the table or your calculator, pause the video and see if you can come up with the answer for this one. I'll give you a hint about the calculator. It's always going to give you a negative number, but you need to be diligent about which answer you give based on what you know about the problem. That was a big hint. Okay, did you figure it out? So we need to find degrees of freedom. N equals 17, so n minus 1 equals 16. So degrees of freedom are 16. It's a right-tailed test, so our number is going to be positive, and it's a one-tailed test, alpha, and alpha equals 0.01. So if we match everything up or type it in correctly, either on the table or in the calculator, we should get 2.583. Did you get it right? Okay, one more. Find the critical values T0 for a two-tailed test given alpha equals 0.10 and n equals 26. Using either the table or the calculator, find these critical values. All right, so the degrees of freedom are 26 minus 1 equals 25. So that is our degree of freedom. It's a two-tailed test, so our numbers, two of them, are going to be negative and positive. And if we're using the table, we need to look at 0.10. But if we're using the calculator, we need to use 0.05 because we're dealing with just one side. Important note here if you're wanting to use your calculator. For a two-tailed test, you need to divide alpha in half before you put it in the calculator because you're only dealing with one side of the graph. Once everything is lined up and you've entered everything correctly, hopefully you came up with negative 1.708 and positive 1.708. The t-test for a mean mu is a statistical test for a population mean. The test statistic is the sample mean x bar. The standardized test statistic in this formula, t equals x bar minus mu, divided by the ratio s, or sample standard deviation, divided by the square root of the sample size. You should recognize this from when we were building confidence intervals for a mean when we didn't know sigma. We still need to check that our sample is random and that either the population is normally distributed or that the sample size is at least 30. So our sampling distribution of sample means is assumed to be approximately normal. So here are the steps for using a t-test for mean mu when sigma is not known. Very similar to the last section when we did z-test, just adjusted slightly because sigma is not known. First of all, we want to verify that sigma is not known. They did not give us population standard deviation. Then we want to check conditions. Is the sample random? Is the population normally distributed? Or is the sample size greater than or equal to 30? If those check out, we move on to our next step. The next step is to state our hypotheses. This is the step we've been doing for a few sections now, writing our null hypothesis and our alternative hypothesis. Remember, we identify our claim, and if it has an equality symbol, meaning less than or equal to, equals, or greater than or equal to, it goes in the null hypothesis. If it has an inequality, it goes in the alternative hypothesis. And then you write its complement for the other hypothesis. After that, specify the level of significance, or identify alpha. Fourth, identify the degrees of freedom, n minus 1. Next, determine the critical values using the table or your calculator. When you have found the critical values, this will form the rejection regions on a graph, less than the negative t0, greater than the positive t0, or both. After that, standardize the test statistic using this formula and sketch the sampling distribution. Next, make a decision to reject or fail to reject the null hypothesis. If t is in the rejection region, reject h0. Otherwise, fail to reject h0. Finally, interpret the decision in the context of the original claim. All right, let's do an example. A used car dealer says that the mean listing price of used vehicles sold in the last 12 months is at least $23,500. You suspect this claim is incorrect and find that a random sample of 14 used vehicles sold in the last 12 months has a mean price of $21,558 and has a standard deviation of 3350. Is there enough evidence to reject the dealer's claim at alpha equals 0.05? Assume the population is normally distributed. First of all, if I'm doing problems, how do I tell this one apart from the ones from the last section? Well, this one doesn't mention anywhere the population standard deviation. It talks about the random sample, its mean, and its standard deviation, but not the population standard deviation, just that of the sample. So that sets it apart from last section's problems. So that's our first condition. It does not have sigma. Now we go down the list. Is the sample random? Well, we just said it was, so yes. Is the population normally distributed, or is the sample greater than or equal to 30? They only used a sample of 14, but they said the population is normally distributed, so we can apply the central limit theorem. Now we get to the claim. What is the claim here? That the mean listing price of used vehicles sold is at least $23,500. So they said at least. That is greater than or equal to. So which type of hypothesis are we working with first? If you guessed null hypothesis, you're paying attention. Thank you. Yes, our null hypothesis will be that the mean is greater than or equal to 23,500. And our alternative hypothesis needs to be its complement, which would be the mean is less than 23,500. So then we think about what type of test it will be. Now, it's been a while, so I'll forgive you if you've forgotten this. Remember, what tail test it is depends on the alternative hypothesis. So because it is a less than, we're doing which type of tail test? Yes, a left tail test. And our significance level? The question said alpha equals 0.05. Since it's a one-tailed test, we keep it at 0.05. How about degrees of freedom? What was n? N was 14, so n minus 1 is 13. So our degrees of freedom is 13. So use the table or your calculator with this information to come up with the critical value. You should come up with negative 1.771. And not just because your calculator gives you a negative number, but because it's a left-tailed test. So the rejection region will be to the left of this value. Now we need to use this formula to find the standardized test statistic using the sample data and assuming mu to be 23,500. And we come up with approximately negative 2.169. Finally, we can sketch the graph and the critical value and rejection region. When we plot the value, we see that it is in the rejection region, so we can reject the null hypothesis. There is enough evidence at the 5% level of significance to reject the claim that the mean price of used cars sold in the last 12 months is at least $23,500. Okay, good job. Let's do another example. An industrial company claims that the mean pH level of the water in a nearby river is 6.8. You randomly select 39 water samples and measure the pH of each. The sample mean and standard deviation are 6.7 and 0.35 respectively. Is there enough evidence to reject the company's claim at alpha equals 0.05? So first we ask the question, did they give us population standard deviation? No, they gave us sample standard deviation, but not population standard deviation. Next, is the sample random? Yes. Is the population normally distributed, or is the sample size at least 30? The sample size is 39, so we can proceed. Now it's time to write a hypothesis. What is the claim? They are saying that the mean pH level of the water is 6.8. So it's equals. So that is which kind of hypothesis? That would be the null hypothesis. So pause the video to write your hypotheses. So the null hypothesis, H naught, is mu equals 6.8. That's your claim. And H sub A is mu does not equal 6.8. Okay, what's next? What does that mean for the nature of our test? Because it's not equals. That means it's a two-tailed test. So what does that mean for our significance level, or alpha? We need to divide it in half if we're using the calculator. if we're using the table, they actually have already accounted for that, and we use 0.05. So we also need degrees of freedom for either one of those. So what was our sample size? 39. So n minus 1 equals 38. So our degrees of freedom is 38. So at this point, use your table or your calculator and the inverse t function to identify your critical points. Pause the video and find those now. You should have come up with negative and positive 2.024. Next, you need to plug all the necessary values into the standardized test statistic formula, assuming mu equals 6.8. Pause the video and do that now. You should get about negative 1.784. Okay, let's see what our graph would look like. We can see where our critical values lie and where the rejection regions are. There's our t-value, the value we came up with when we put all that information into the formula for the standardized test statistic. We did that to test the data, to see where it fell in the rest of the data. So would you reject the null hypothesis in this case, or would you fail to reject it? You would fail to reject it because it does not lie in the rejection region. It's just outside of it. Okay, we're going to do one more example, but this time I'm going to show you another calculator shortcut. A Department of Motor Vehicles office claims that the mean wait time is less than 14 minutes. A random sample of 10 people has a mean wait time of 13 minutes with a standard deviation of 3.5 minutes. At alpha equals 0.10, test the office's claim. Assume the population is normally distributed. So we still need to check for conditions. Did they give us population standard deviation or sigma? No, just sample information. Is the sample random? Yes. Is the population normally distributed, or is the sample size greater than or equal to 30? They said the population is normally distributed. Good, so we continue. So we still need to come up with hypotheses also. What is our claim? That the mean wait time is less than 14 minutes, so less than, which is an inequality. That means our claim is in the alternative hypothesis. Pause the video and write those hypotheses. Hopefully this is what you got, that the null hypothesis is mu is greater than or equal to 14 minutes, and h sub a is less than 14 minutes. Okay, after that we're ready to use the calculator shortcut. To find p-values for a hypothesis test, do the following. Press the Stat button, arrow over to Tests menu, then select the number 2 option, t-test. Then you want to highlight Stats. It may already be highlighted, or you may need to arrow over to highlight it. Then you need to enter the values for the following. Population mean or mu, sample mean or x-bar, sample standard deviation or s, and sample size or n. After that, select the appropriate inequality symbol to go with your alternative hypothesis, then choose Calculate. You should get something similar to what you see on the right. Pause the video for a moment if you need to practice this, or make notes for yourself wherever you keep your calculator notes. From the display, you can see that p is about 0.1949. Because the p-value is greater than alpha equals 0.10, you fail to reject the null hypothesis. There is not enough evidence at the 10% significance level to support the office's claim that the mean wait time is less than 14 minutes. Okay, another section done. Great job. I'll see you on the next video.